Oh, okay. Well, I mean, I started reading the textbook you sent me, but I haven't really gotten to go like as in depth yet as I
Yeah,
wanted
yeah,
to, as I would have wanted to because of school. So
yeah.
when I graduate this year, I'm planning to like take it more seriously, get more into that.
Okay. Like intro to like the world art.
Okay. Yeah, sure.
Yeah. So basically, kind of where everything started with like deep reinforcement learning. Um. All right. So let me see if I have. Yes. Um. Let me share my screen. Yeah. So. All right. So basically, what's reinforcement learning in a nutshell? So I mean, it's the whole idea of learning through trial and error, right? So you basically make some attempts at some task. So how would that look? So it maybe take some action in some environment. You would receive some reward, and the whole idea is that you're trying to reinforce the actions that give you good rewards. So if you can imagine trying to train your dog to say do a trick, usually what you do is if the dog did the trick correctly, you'd give it a treat. Didn't do it correctly, then it wouldn't get a treat. Or if you've ever seen those movies where they're training monkeys to do these tasks, then they get a treat when they do it correctly. They would not get the treat when they do it improperly. And it basically resembles how humans learn in a sense. So we have our own reward signal in our brain called dopamine. And whenever we do things that um, basically things that we need to do on a daily basis to survive, so things like eating, we get a dopamine rush. So basically, that's a pleasure chemical that reinforces that, hey, eating is a good thing so that we can continue to survive. So it's the same thing here. We are trying to use that same idea of learning through rewards and reinforcing the actions that led us to get those rewards. So basically, what you're trying to do is to, at the end of the day, learn some sort of policy. So policy is basically, think of it like a rule set. It says if I'm in a certain state, what action should I take? State is basically what the agent perceives, or however the agent perceives the environment. So it could be measurements from, say, a LiDAR sensor. It could be images coming into a camera. As I said, the whole idea is that if I'm in a particular state, what action should I take? Right? So if, for example, I'm sensing that there is a obstacle in front of me, what action should I take? Should I continue going forward, or should I move to the left, move to the right? And basically, the idea is that you're trying to learn that um, through trial and error, um, by getting rewards, what actions to take in what particular state. So the idea is that basically you want to learn a policy that will maximize your cumulative reward at the end of the day. So what how do we go about doing this? So I mean, reinforcement learning is big in the machine learning community, especially nowadays, because of a lot of the cool things it has done um, lately. So I guess I may just take it through the history of it. Um, in around 2015, let me look for a GIF. Yeah, so reinforcement learning is not something new. It's actually a technique that has existed since about 19 around the 90s. So researchers like what's his name? Mm, mm, yeah, the name is escaping me. But yeah, reinforcement learning research has been going on since basically the 1990s. So it basically, started out with the whole idea of temporal difference learning. The idea is that, each time you take an action and get a reward, you basically try to update the policy, and you basically updating the policy such that the next time you essentially try to maximize the reward that you're getting. So the reason why it's actually been like a big thing of late is that like in about 2015, Google DeepMind had the idea of pairing reinforcement learning with neural networks. So reinforcement learning in the 90s didn't really use neural networks. So vanilla reinforcement learning basically, think of it like you would have a table where you have states, actions, and then essentially what you did was update that table and learn some sort of what we call a value function, which is basically if I'm in a particular state, what's the expected return or what's expected sum of rewards I should get given that I'm in a particular state. So that worked on very simple problems, but when it came to problems that involve very high dimensional data, such as problems where the state involves, say, an image or something like that, that's where reinforcement learning basically proved not to be so effective. Because, for example, something like an image where you can have many possible and infinite possible amount of states, you basically can't represent that in a table format. It's just going to be impossible. So what they did was actually pair reinforcement learning with neural networks. So basically what they did was use a neural network to process the incoming image, and that would create a state from that. And then the neural network would be responsible for essentially predicting um, a sort of value for that state. And they found that this worked pretty well. So in 2015, they tried it on a bunch of um, classic Atari games. So this is one example with Breakout. And the cool thing is that, it learned to do all of this entirely from scratch. So generally with AI programming, um, either it learns from human data or you have to program it directly to do what you want it to do. But with this, it learned entirely on its own. So there was no playbook or any rules programmed into it. It literally learned entirely from trial and error how to play this game properly. So the only thing it had access to was the image coming in from the game screen, so what you're seeing right now, and the score. So the score would essentially act as a reward. And through that same thing, that iterative thing of taking actions, getting a reward, updating your policy to maximize the rewards, it, you know, it was able to essentially perform even better than humans at some of these games. And from that, that basically just caused an explosion with deep reinforcement learning. So what came after this was um, Go, AlphaGo. So yeah, so I'll, the game of Go was seen as basically one of those untouchable games, kind of like how chess was seen in the 90s, where they were basically saying that, a, a machine could never beat the grandmaster at chess. They said the same thing about Go, that it would basically take up probably another 10 or 15 years before a computer would be able to beat a grandmaster at the game of Go. But it turns out I think it's around 2016, using the same technique I mentioned a while ago, reinforcement learning. They created this program called Alphago, and it actually, again, through the same thing of learning through trial and error, self-play. So it played games against copies of itself. It learned to play the game of Go at basically a grandmaster level. So it surprised the world of Go because AlphaGo beat Lee Sedol, basically the world champion of Go at the time, 4 games to 1. So that completely shocked the Go community. The reason why it shocked the Go community, Go is kind of, well, it's unlike chess. So chess has a set number of moves, set number of positions. Just like Go has the same set number of moves, set number of positions. But the thing with chess, the number of possible board positions is a whole lot smaller than it is for Go. So I think for Go, basically the number of possible board positions is on the order of like about 2 to the 100 or 2 to 140. Basically, to put it into perspective, there are more possible board positions in Go than there are atoms in the universe. So basically, unlike Deep Blue, the program that beat Gary Kasparov at chess, where it basically simulated board positions and did some crafty things with like alpha beta pruning and tree pruning, stuff like that. You couldn't do the same thing with Go because there's just too much states to represent. So they basically said the only way humans could play Go, or reasons why humans can play Go the way they can, is through simple human intuition, right? So human intuition is not really something you can explain. It's not really something that you can jot down and say, do this, do that, do that. It's basically just something that you come up with. So it's very hard to put down on paper. So that was one of the reasons why they were like, yo, there's no way that AlphaGo can replicate that. It turns out it did. I'm not gonna say that what it did was on par with human intuition, but it definitely simulated that same thing. So it did some surprising thing. There was actually one game where it did, I think they call it the God move. So there was a move that everybody thought was like a really stupid move. Like, why would it do that? But it turned out to actually win the game. So the whole thing about reinforcement learning is, or the promise of reinforcement learning is the ability to learn on its own. So usually you would have to either get expert human data and the machine would essentially try to replicate that. Problem with that is gathering data is a chore, so we're trying to cut that out. Second thing is if you're trying to model expert human data, the policy that you learn is basically limited by that expert. So however, so that's your threshold. You're basically only gonna get as good as the expert. But reinforcement learning, because it's learning entirely on its own, then there's that promise that it can learn something even better than what a quote unquote human expert would do. And it has proven to do that, just like with the Atari game, and with this. So I mean, from this, as I said, there's been an explosion with deep reinforcement learning. So there's a bunch of environments that they benchmark reinforcement learning algorithms on. So basically, it started out with DQN, and then from there have been some improvements on that. So what I'm going to go through today is actually that first reinforcement learning algorithm, DQ learning. Um, and basically, as I said, from there, there's been some improvements on that particular algorithm. Um, Let me see. There's one where they used it. I know OpenAI used it too on their finger. Was it Dota? Yeah, so companies like OpenAI, which is another research group, use it to play these sort of real-time strategy games. Um, I know DeepMind recently did the same with StarCraft, and they call that one Alpha Star, right? Um, and there are a bunch of different environments that they benchmark these algorithms on. So the most famous environment or library that we use for reinforcement learning is this. So the gym. So if you're gonna do reinforcement learning, definitely this is gonna come up. Gym. So there are a bunch of different environments. So the same Atari environments that I was saying or mentioned earlier, you can access those. There's some other environments like pendulum, mountain car. Yeah, the easiest environment to start out is this one, the carpool one. So if you actually go on the OpenAI site, Jim, yeah. So it's a very simple library to use. So after you import it, you can essentially um, use any one of the environments. It has a very simple API. So as I said, with reinforcement learning, you basically take an action, you get some reward, make some observation, and then the loop continues. So that observation is basically the state that I was mentioning earlier. As I said, the state could be an image. The state could be just some numbers that represent maybe joint angles, depending on if it's a robot or something like that. And then you can do stuff like reset. So it's basically like start over the game and stuff like that. So what I'm going to show you today is basically how we can use this OpenAI library called GYM to create a reinforcement learning environment. And from that, use the DeepQ network or the DeepQ learning um, to, to see if we can solve this environment. So there's usually like a certain score that we consider solving the environment. So if the agent more or less averages that score, then we can say it solves the environment. So we're gonna see if we can train an agent to basically learn from scratch how to do a particular task. So the task that we're gonna use is, or the gonna do is this one, cartpool. So the whole um, or whatever what it's trying to do for this particular environment is essentially balance a pool. So just imagine trying to like balance a stick on your hand. So you kind of have to, move your hand back and forth to keep it, um, stable. That's basically the same thing here. So with this, you have two actions. You either go to the left or go to the right, right? And your observation you get is basically some, angles of, what's the angle of the pole and stuff like that. And basically, given that information, can you choose the right action to keep the pole upright? The game is lost when the pole basically falls over. So the longer you can keep the pole upright, um, the the more points you get. So we're gonna see if we can actually do that. All right, so let me go to find the paper. What I'm gonna do is to look at the original DQ learning paper and see if we can go through that paper and replicate the results. All right, so they have the algorithm here. So essentially what we're gonna do is to implement this algorithm right here. Um, and see if we can replicate some results. So this paper, I would recommend if you're getting into reinforcement learning, to actually read this paper. So this is the paper you should start with. Reason being, it's the simplest one, and it will give you a good base to continue learning reinforcement learning from here. All right. So I guess let's get right into it. So as I said, reinforcement learning has existed since the 90s, right? Um, so there's actually a good book. Let me see if I can remember the name. Reinforcement learning. Ah, yes. His name is Richard Sutton. So yeah, this is a guy. He wrote this book, Reinforcement Learning. This him and this guy named Andrew Barto. Yeah, I'd definitely say take a look at this book. So these are like the main guys for this field. So they're the ones that really are the pioneers of reinforcement learning. All right, so I guess let's look at a particular reinforcement learning algorithm. So you have something called Q learning. All right, so the whole idea with Q learning is that you're essentially trying to learn what's called a Q function. So a Q function basically, given a particular state, given a particular action, what's the expected return on that? So let's think of it in terms of, say, a game. Let's say you're playing chess and you have a particular board position. So that's, say, your state. If I move, say, one piece from one part of the board to the next, what's my likelihood of winning the game? Right? So that could be like literally a 1 if you're likely to win it, a -1 if you're likely to lose, or 0 if it's going to end up in draw. So the outcome or the reward might not be so discrete, meaning if it's a win, lose, or draw, the reward might be like points. So like, for example, if I'm playing something like Space Invaders, for example, and there's an alien there and I shoot, what's the likelihood, or not the likelihood, basically how much points am I likely to get when this game ends? So essentially that's what you're trying to do is learn a Q function. So the whole point of the Q function is, it given a particular state and an action, it's supposed to can predict what's the likely return. So like how much reward, what is the sum of rewards you're gonna get from this particular state until the game ends. So of course, the actions that lead to greater cumulative rewards are the ones that you would want to choose. So the whole idea is that if I'm in a particular state, you look at your queue function for all the possible actions, and then you choose the action that has the highest queue value. How do you go about learning this queue function? It's basically using this formula here. So the idea is that you start out with a table. So let me actually show you an example. I think the best way to do this is using a whiteboard. Yeah, so okay. Yeah, so let's just say, for example, you have some states here, right? So let's just use some numbers, so 0 and 1, right? And let's say in terms of actions, we have A and B. Okay. So basically, you're trying to learn what's called a queue function, right? So given a particular state and an action in that state, what is what's the cumulative reward I'm expected to get from this position? So let's say, for example, I just started out a game. What's the expected number of points I'm expected to get when this game is finished? All right, so basically what happens is that the Q values start out with some random values. So let's say, for example, start out with some random values here. Yeah, so as I said, with reinforcement learning, you're in a particular state, you take some action, and you get some reward, right? So let's say, for example, you're in state A, and you take, say, action 0. Let's say for that transition, you get a reward of, say, I don't know, say plus 3, right? So basically, the updated value for this would be using this formula here. So it's whatever the previous Q value is for that particular state, taking that action, that'll be 0.1 plus whatever the learning rate is. Let's say, for example, the learning rate is like, say, 0.5. And then it is the reward that you get. So let's say 3 plus a discount factor. I'm going to leave that out for now. But the important term is this. So it's whatever the max for the next state. So this is basically saying, right? So if I'm in a particular state, right, I take a particular action, right? What's the state that I end up in? So let's say I'm in state A, I take a particular action, let's say that's 0. What's the state I'm going to end up in? So let's say I end up in state B, right? After I take that particular action.
quick question.
Yeah.
So are all of the states initialized to the same value, or is it just like a random distribution? Because I noticed that
Yeah.
all of
Well,
them are
it
the same.
it depends. So it's entirely up to you. Just like how you would like, how you choose to initialize a neural network. It's the same thing. So you could basically initialize all of these to zeros, or you could just give them some random values. So yeah, I think yeah, you could basically just give them some random values.
Okay.
Yeah.
Okay. And so is the output space of actions usually like discrete, like these are?
Yeah, good question. So it depends on the problem. So for vanilla reinforcement learning problems, the states are discrete and the actions are discrete. Now, for most real-world scenarios where the states and actions probably aren't discrete, that's where deep reinforcement learning came into play. The fact that those states aren't discrete means that we can't represent it like this in a table format, which is why we now had to introduce the whole idea of a neural network to basically make a direct prediction from the state. So vanilla reinforcement learning worked on simple problems that involve discrete states, discrete actions. Most real world problems aren't like that. That's how deep neural networks came into play to help out with that problem. So for this particular problem, we have discrete states, discrete actions. So for some problems, you actually find that the state, sorry, not the state. You find for a lot of problems, the actions are discrete. But there are also some problems, like some robotic problems, where the actions are actually continuous. So it could be like, the action could be like a steering angle, or it could be something like, I don't know, the amount of force you apply to a pedal or something like that. But the very simple reinforcement learning problems are actually discrete action problems. So like for the Atari games, those actions are discrete. So like you're either moving the paddle to the left or to the right, right? All right, so yeah, basically the idea is that you just follow this update rule, right? So the new Q value is whatever the Q value was before, plus we'll have some learning rate. This learning rate is basically the same as with for like neural networks. It's basically how fast we learn the Q function, right? So the idea is that we don't want to update our Q function too rapidly, right? Because at the end of the day, you're trying to make a prediction, right? So we don't want to update our Q function too rapidly. So what we do is have this learning rate to say, hey, just update it more steadily. So don't update it very fast, just update it steadily. So if you look at what's in the bracket here, so they call this the temporal difference. So the updated Q value should be the reward that you get plus whatever the Q value is for the next state, right? So we have our Q function here. So it has 0.1 for this, 0.1 for this, 0.1 for this, 0.1 for this, right? So these are the Q values for these particular states and actions. So it's basically saying, all right, let's say I'm in state A. I take this action 0, right? So the Q value for that state action is currently 0.1, right? So you're saying it's 0.1 plus whatever the learning rate is multiplied by, in fact, let me approach it from a different angle. The new Q value is really supposed to be this. So it's whatever reward you get plus the max Q value for the next state. Right? So you're gonna get an action. You're in a particular state, you take action, you get a reward. You get a reward of, let's say, +3, right? So you get a reward of +3. You're trying to predict what's the cumulative, or what's basically my final reward when I end, or what's my final sum of rewards when I end this game. So let's say I start in A, take action 0, end up in B. I take action 1, end up in A, take action 0, end up in B, so on and so forth. And let's say you get some rewards for this, right? So let's say you get +3 for this, let's say you get +4 for this, you get +3 for this. Basically, my Q value here would be the sum of these rewards. So let's say the game ends right here, right? So this is basically the Q value here is 3 + 4, 7, 10, right? Should be around 10. But that's basically saying, all right, I'm in this particular state and I take this action. What's my likely final score, right? So I'm gonna get, at the end of this, I should get 10. Let's say we went a different route. Instead of taking action 0 here, we took another action, we ended up in another state. And let's say by the end of this, we ended up with, say, a final score of, say, I don't know, 12, right? This is basically saying, if I'm at this state, I take this action, then I'm likely to end up with a final score of 10. If I'm at this state and this action, I'm likely to end up with a final score of 12. And that's basically Q learning in a nutshell. You're trying to learn this Q function that can predict what more or less what your what's the sum of rewards that you would get from this state, taking that particular action. And once you've learned that Q function, then you can use that Q function as a guide to basically solve the task. Because at the end of the day, once you've learned your Q function, you're essentially just going to take the actions that lead to the highest Q values. So if I'm in a state and I'm wondering what action to take, I'm just going to consult my Q table and just take the action that has the highest Q value. So this is basically, yeah. So instead, I can print the final reward. Person. Yeah, so now it's printing the the actual points or how much it got at before it fell over. So the highest we got was 52. To solve this environment, you need to be getting about 200. All right. Yeah, so as I said, there are different environments. To explore the different environments that you can get, you can come here to environments and basically choose whichever one you want. All right, so depending on the task that you're trying to do, if you want atari environments, then you have a bunch of them here. A bunch of them. So you basically just copy and paste the environment ID, paste it into there, and you're good to go. If you're more into, say, robotics, then you also have these environments. Yeah. There's also something called musical. You want these type of environments as well. So all of these are reinforcement learning environments. Yeah, where was that? Yeah, so that's basically how you would render the environment. So coming back here now, so after you define the environment, so yeah, so as I showed you before, this is what you get back when you make an action in the environment. And this is what we essentially just did a while ago. Just taking some random actions, getting a reward. All right, so remember I said you have like transitions of state, action, reward, next state, right? State, action, reward, next state, state, action, reward, next state. The idea is that you want to collect all of these into what we call a replay buffer, right? So remember I said, basically you're gonna use all of this to create predictions and targets. Using supervised learning, you're gonna basically learn a Q network or a neural network that represents the Q function, which you're going to eventually use as your policy. Now you're gonna collect all of those transitions. A transition is just basically a state, action, reward, next state, action, reward, next state. You're gonna collect all of that into something called a replay buffer. And the idea is that you're gonna collect all of these experiences in a buffer, and then you're just gonna take a random sample from that buffer and then train your neural network on that. So right here is basically just adding some experiences to the buffer. So we'll have the same loop set up. So we're running 10 episodes. And you're saying, all right, while the episode is not done, sample a random action from the environment, take that action, you're gonna end up with a state or reward, whether the episode is finished or not. And then you're gonna pass all of that to the replay buffer. So the state of course starts out like this. The action that you took, which is this, the reward that you got, the next state, so what state did you transition to, and whether the episode was completed or not. All right, then you add the reward that you get to like a sum, and then importantly, don't forget this step, is to set the current state to whatever the next state was. So of course, if you start from A and you transition to B, then your current state is now B. So that's what this line is doing. All right, and then you basically just add a bunch of these to your, so represent this like as a tuple of state, action, reward, next state, whether the episode is complete. So all of these are going to be important to calculating our predictions and our targets, so we can use those to train our Q network. So this is just showing you a sample of our replay buffer. So this is the first thing in our buffer. As you can see, we have here a state, a reward, a state, a reward, a state, an action. So the action we took was 1, a reward, the next state that we ended up in after that, and whether the episode was complete. All right, so the next thing now, remember I said a neural network is gonna represent that Q function. So we're gonna create a neural network in, what is it? We're going to create a neural network using Pytorch. So creating a neural network in Pytorch, you basically create a class, and that class has to extend this, the nn.module, this class here. And then this is what you call a constructor. And basically you're just calling the super from that. And basically this is how we construct the neural network. So basically, you can choose what type of layer it is. So it can either be a convolutional layer, a linear layer, which means it has no convolution. So here I'm saying, all right, the first hidden layer is gonna have 200 neurons. The second hidden layer is gonna have 300 neurons. The output layer is gonna have 2 neurons. Now you're probably wondering, why do these numbers seem to repeat? So I have 200 here, 200 here, 300 here, because you have to specify how many neurons it's gonna accept. So from the input layer, which is basically how many neurons in your input layer, you're gonna have usually as much input neurons as there are states, or the dimensions for your state. So as you can see, this array here has 4 dimensions. So this. So we're gonna have a neuron to represent each of those. And that is going to connect to the first hidden layer that has 200 neurons. Then that first hidden layer is gonna connect to the second hidden layer. So that's why you specify that it's gonna accept 200. That has 300 neurons. So I have 4 to 200 to 300. And then the last layer is a 300 to 2. All right, so that's how you define your neural net. And then basically this function forward is basically you defining the forward propagation of the neural network. So you're taking a state, and then this is you telling how the neural network should calculate its output, which is why I like Pytorch, because you can basically customize exactly how this happens. So here we're basically saying, all right, use the first hidden layer, taking the state, use the first hidden layer. That's gonna process that. And then this is how you specify the nonlinear activation. So you import this here, this function, torch.nn.functional, and then we'll import it as f. And then you can say f.relu. So we're using relu nonlinear activation here for this particular hidden layer. And we're doing the same thing for this. So pass the output of this to the next hidden layer, the output of this to the output layer, and then return the output. All right. So after you create the neural network, how do you use it? Well, you create an instance of that class like this, and then basically you can use the neural network. So here we're just showing an example of how we do that. So I'm just sampling a random state from the replay buffer. So for the first experience or transition, which is this, we're getting the first thing from that, which is a state here. And so we execute that just to show you. Oh, I need to run some stuff here. All right, so we'll have the state here. Now, this is an array, right? So the gym environment, these return NumPy arrays. But for you to use your neural network, it needs tensors. So you need to convert that NumPy array to a tensor. So that's where the from NumPy function comes in. So it's a torch.from NumPy, passing a NumPy array, and we'll convert it to a tensor. So this is how it looks now. So instead of saying array, it now says tensor. Okay. And there's things you can do. You can select shape. Oh, I need to run this. and this. If you want to see the shape, so this is saying this has 4 or just a flat 4-dimensional, or you can see the actual tensor. You can reshape it. So I can say something like reshape. Let's say if I want it to be a 1x4, it's not reshape, view. So let's say I want it to be a 1x4, then the function to do that is view. So this is reshaping it from just a flat 4-dimensional to a 1x4. All right, so basically now I'm passing that tensor that I just created, converting it to a float tensor, passing it to the neural network. So as you can see, what the neural network outputs, it outputs an array, 2 values. So remember I said the Q function is we're going to represent it using a neural network, and then it's going to take in a state, and then it's going to basically make a prediction for the Q value for that particular state for all the actions that are possible in that environment. So there are 2 actions possible in our environment, right? So it's going to output 2 values, 2 Q values. So 1 for each possible action for that state. All right. So let me, I guess, go through how this is going to work. So they explain it here. So this basically is what I was referring to earlier, where we have targets and we have predictions, and we're going to basically put that in a loss function. All right, it's like mean squared error. So that's what they're showing right there. But let's go to the actual algorithm. Here they talk about the replay memory that each experience inside this, just a tuple where we have the state, action, reward, and the next state. I'll place it all into the buffer. But yeah, this is a basic algorithm. So we're initialize replay memory. So we just did that a while ago. So we're basically going to create a Q network to represent our Q function. So here it's saying, all right, so for each action or each step for a particular episode, so for each episode, for each step, so a step just corresponds to an action. So we're going to select a random action with probability E. So this is what we call E greedy selection. So basically, with some probability, we're going to choose a random action or choose the greedy action. So the greedy action is basically, as I said, eventually we're going to lean on the Q function to decide which action yeah, so remember I had said earlier, we're gonna lean on the Q function to eventually decide which actions to take. So this is what I was referring to. So basically we start out choosing random actions, but eventually we're going to be choosing the greedy action, which is basically what's the action that has the max Q value, right? You execute that action, you get some reward, you end up with the next state. You add all of this to the replay buffer, right? So the state, the action, the reward, and the next state. Then you're basically gonna sample a batch of transitions. Remember, transition is state, action, reward, next state. You're gonna sample a batch of those from your replay buffer and calculate targets for all of those. So it's saying here, for those where the episode was finished, so where episode done equal true, the target is just the reward that you got. If it is not, so episode done is false. So if we go back here, remember you get back this, a signal as to whether the episode is finished or not. So it's saying basically if you sample from this and you calculate in the target, If this is equal to true, then the target is just the reward. If it's not, so if it's false, then the target is this. So it's whatever reward you get plus gamma multiplied by whatever the max Q value is for the next state. And then once you have that, your predictions and your targets, you essentially perform gradient descent using some loss function like mean squared error. And that will update the neural network. And it will just keep doing this. All right, so we're gonna see how that looks now in code. All right, so we created a replay buffer before that's gonna store all our transitions. What we did here was just take some random actions just so we can have some stuff in our replay buffer. Starting it out, we created our neural network. So using Pytorch here to create a neural network. So this neural network is just a multi-layer perceptron with 200 neurons in the first hidden layer, 300 in the second hidden layer, 2 in the output layer. And we just showed an example how you can create a neural network here and how it can accept a tensor and what it outputs. All right, so as I said, it's gonna use the E-greedy strategy to decide which actions to take. So what do I mean by E-greedy? So with some probability E, it's gonna decide whether to take a random action or not, all right? So basically you're going to use like a random number generator to come up with a random number between 0 and 1, right? You're going to have some number E that represents the probability of choosing a random action. If the random number that you generate is greater than E, then you pick a random action. If not, then you pick the greedy action. So usually E starts out, I think, as a big number, yeah? So which means that you'd start out picking mostly random actions, and then eventually E gets smaller and smaller. So you are more likely to choose the greedy action, right? So that's the E greedy. So what I did was create a function here that basically what this does is we'll have a start for the E value and a min value for the E. So this is basically saying when E is 1.0, this is basically saying there's 100% chance that it's gonna choose a random action, right? When it gets here, this is basically saying there's a 20% probability of choosing a random action. Or read it the other way, this is saying a 0% probability of choosing the greedy action. This is saying 80% probability of choosing this is saying 0% probability of choosing the greedy action. Here it's saying 80% probability of choosing the greedy action. All right, so we'll start off with this, and then we eventually make this smaller and smaller and smaller and smaller. So eventually this gets to a higher probability of choosing the greedy action. And we just use whatever the number of steps is currently to decide that. Here we have a function that basically just samples from the replay buffer. So remember, the replay buffer is just a list. So it's basically just gonna shuffle this and then get the first 32 instances from that. All right, so here I basically instantiate my Q network. So this is what we're gonna use to calculate our predictions. And then we have another network that looks just like our prediction network to calculate our targets, right? So they're basically the same thing. 2 instances of the same network, right? And basically, as I said, we're gonna use some sort of gradient descent. In this case, we're using the Adam optimizer to optimize our neural network. So basically, this is how you do that in Pytorch. So you have to create the optimizer, pass in the parameters that you want to optimize. So we're optimizing the parameters the prediction network. This is the learning rate. And target network, we're just gonna basically initialize the target network to be the same as the Q network. So basically what's gonna happen is that the target network is going to lag behind the prediction network. So basically the reason why we did that, and they explained it somewhere in the paper, is that for supervised learning to work, the targets have to essentially be stable. So basically what we do is have a separate target network that lags behind the prediction network, that allows us to get a stable target to get to. Think of it like this. Think of aiming at like you're doing like a shooting contest. It's the difference between shooting at a target that is still versus shooting a target that is moving. Obviously, a target that is moving is going to be a lot harder to hit than something that is still. So that's what we're doing here. All right, so we're just basically following this loop here. That's defined inside the paper, the DQN paper. So we're following this loop. So this is how it looks in code. So basically we just have a maximum number of steps that one take in the environment. We could have written it differently where we just do it for a certain number of episodes. Really up to you how you want to phrase this loop. So basically we're saying, all right, for each episode, do this. We're gonna decide whether we're choosing the greedy action or not. So this is gonna use the eGreedy function. It's gonna pass in whatever the number of steps we are at currently. Clearly, the closer we get to the max number of steps, the more likely it is that we take a greedy action. So we'll start off with likelihood of taking a random action being higher. As we get further and further along, it should get more likely to take the greedy action. So more than likely, this is gonna be a random action when it starts out. So this is me taking a random action. This is me taking a greedy action. As you can see, for the greedy action, what I do is use the Q network to predict what action I should take. So I pass in the current state here, use the Q network to make a prediction. And then this function here is just gonna get me the argmax. So basically, remember what the Q network calculates is this, the Q value for each action. We basically want to see which action had the higher Q value. That's why we say argmax. So it's basically which index. This is gonna give me the index position of the higher value. So if basically action 1 had the higher Q value, then it's gonna give me back 1. So that action now I pass to the environment, which is gonna give me back a state, a reward, and whether the episode was completed. Remember, this is gonna be important when we're calculating the rewards, because when the episode is the target is gonna be different for terminal episodes that are transitions that are terminal versus ones that are not. Terminal just means whether the episode was completed or not. So yeah, so basically take an action, next state, reward, whether the episode is done. This is me just adding the reward to like a sum so I can record how much points was achieved in a particular episode. So that said, you're going to, as the algorithm suggests, you're going to the state, the action, the reward, the next state, you're gonna store that inside the replay buffer. So that's what we're doing here. With the state, action, reward, next state, whether the episode is completed, we store that in the replay buffer. And then of course, the state now becomes whatever the next state is. Now, basically what we want to do now is to update our Q network, right? So remember, Q network represents our Q function. Q function represents the policy that decides what actions we take for particular states. So that's what this is doing here, right? So after a certain amount of steps, so every 4 steps, we're gonna allow the neural network to learn. So what it's gonna do first is to sample from the replay buffer. So it's gonna sample 32 transitions. So it's just gonna be a batch. And then what I'm doing here is to get the states from that, the actions, the rewards, the next states, and whether the episode is completed or not. Here, what I'm doing is basically just converting these to tensors. So I convert the states to tensors. And then I pass that to the Q network to calculate the Q values. So this is going to represent our predictions, right? Yeah, so this is me basically. So remember the Q network is going to return something like this. But what we want is a Q value for the actions that we took. So this is me actually getting the actual Q values for the actions that we took in this line here. So this is saying for each Q value that we get back here, give me the actual Q value for the action that we took. So remember the Q values is just a list of Q values for each action. So it's gonna look, it's basically a list of these. And then you want basically what's the Q value for the action that you took. So if you took 0, then this is gonna be the Q value. If you took 1, this is gonna be the Q value. So that's what you're doing right here. All right, so the next thing is basically to calculate the targets. So these are all the predictions. Now we need the targets. This is me calculating targets. So basically I'm going through each transition. So here I'm saying, all right, if this is a terminal, so if the episode is done, just like the algorithm says, the target is just the reward. So that's what I did here. Else, the target is the reward plus gamma times the max Q value for the next state. So I use the target network now to calculate the Q value for the next state. And then here, this is me just finding what the max Q value is for that next state. All right. And then I append all of these targets to a list. Then I convert that list to a tensor. Now this is me defining the loss function, right? So this is the mean squared error loss. And then what I do is pass the predictions and the targets to the loss function, and this comes back with the loss. Now this loss here actually represents a tensor. So what you can do is do back propagation from that tensor. So it's gonna do back propagation and then update all the tensors that were involved in calculating this loss. So in this case, it would be this, the Q action. And then here I'm basically just updating the parameters of the neural network. So this is me just zeroing out all the gradients. This is me doing back propagation. So this is going to recalculate all the gradients. And this is basically updating the parameters with those gradients. And then after every so amount of times, I'm going to match the target network with the prediction network. So I don't want the target network to fall too far behind the prediction network. So after a certain amount of time, I match the target network to the prediction network. And then I print the reward for each episode. So let me actually just run each of these, see if it works. All right, so you should say the score is being pretty bad starting out. So as you can see, we'll have some 50s because the steps pretty low right now. But as the steps get higher and higher, you should see these rewards getting better and better. Because right now it's taking most of the random actions. So remember, it's deciding whether to take a random action or the greedy action. But as soon as you get higher and higher in these steps, the probability of taking the greedy action should get higher and higher. So these scores should get better and better. So as you can see now, we're getting some hundreds. So the score that we're looking for is say an average about 200. So it solves this environment pretty quickly. So once you start getting those 200s, you know that we're pretty good to go. As you can see, we're getting 200, 200, 200, 200, 200. So we can be pretty certain now that this has learned the environment. Yeah. So once you get about like 10 of these right or thereabout, you can be confident that it learned the environment. And it did it pretty quickly actually. It took about 13,000 steps. Yeah. So this is actually one of the simpler environments to solve actually. Yeah. So what you can actually do from here is to save the parameters of the net, and then unluckily I can't show you the what it would look like in I guess what I could do, let me see. All right, let me copy this to let me download this so I can actually run it. Download. Or maybe yeah, let me just run the let me download the IPYNB or the Pi, yeah. Yeah, let me see if this works. Download. So just to kind of show you what it would look in the output, I'm going to actually run this file here, but I'm going to render the environment. I'm going to say env.render. Let me see if this works. Yeah, so this is it actually training right now. But it's clearly going to train a lot slower than it did. That's why people don't usually render the environment when they're actually training it, because it actually moves a lot slow to render when you're rendering the environment. So this is actually it trying to balance the pool. As you can see, it's like it's kind of getting, every time you see like it reset to the middle, that means it basically fell over. So hopefully this gets close enough to, so this is the output, this is the, well, this is the how it's rendered, this is the reward. You can actually also graph this using something like TensorBoard. The same thing they use at TensorFlow.
I didn't know that you could use TensorBoard with Pytorch.
Yeah. So there's something called TensorBoard X, which is like TensorBoard. It's basically TensorBoard for Pytorch, or it's a port of TensorBoard for Pytorch. So you can see how you see. Yeah, so this is it, learning. So as you can see, it's kind of learning now to kind of maybe go to the left, try and stabilize it. Yeah, it's getting better. Yeah, look at that. Yeah. Yep. pretty cool stuff. Yeah, 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 definitely, yeah. Yeah, it's very fascinating. Like it's almost like you're just seeing intelligence in action. Um, so this thing getting smarter and smarter all on its own. It's very fascinating. How a simple algorithm like temporal difference learning can lead to something like that. Yeah. It's almost like seeing a baby learning to walk. Yeah. Learning its first steps. Yeah, pretty cool. Yeah, and that's it. I don't want to
So
speak
like,
less.
so like, how much more complicated would this get when you're applying this to a real robot or something like that?
Um, complicated, I won't say much more complicated. Like you can use the same algorithm here to actually train a real robot on some tasks. Um, of course, again, it depends on what the state is gonna be, how you're gonna represent the state. Is it just gonna be like LiDAR measurements? Is it gonna be are you gonna be using camera? It's entirely up to you. To be honest, anything that involves a camera is gonna make your life a lot harder. Because that's gonna involve you trying to train a convolutional neural net, is complicates the issue. If it's like, just um, just some measurements from sensors and stuff like that, like probably ultrasound sensors or whatever, then that's an easier task. But if it's something like from a camera, then that's a much harder task.
Well, couldn't you like one plus one could like uh so like with the camera,
Yeah.
would you have to learn like some representation of the world like with an autoencoder or something and use that to train the network, use the output of that to train the network?
I mean, you can, but I mean, you don't have to. I mean, you could start out with just passing the image directly into like a convolutional neural network, and then it do the same thing where it calculates some prediction. But the problem with images is because there's so much different, you know, possibilities for an image. Learning that Q function, it's just gonna take longer. It's not that it's not gonna learn it.